Hi, Physics 100 students. It's Dr. Ricardo here. We are going to do probably what's just going to be one lecture on nuclear energy. It is chapter 7 in your book. And the first thing that I want to talk about is why we can harness nuclear energy in the first place in order to create electricity. So it turns out that it's not a chemical reaction at all. It's a nuclear rearrangement that occurs inside the nucleus of atoms. And the most stable atoms turn out to be ones with a mass number between 50 and 100. So they're going to be the ones that are highest on the chart. In fact, this one right here, iron that has 56 nucleons, turns out to be among the most stable elements on the whole periodic table. So let me quickly go through all of these examples here and tell you what these numbers mean, because you may not have seen them. Okay, so I'll do the iron 56 one first. So here's the number that we write on top is called the mass number. So that means there are a total of 56 protons and neutrons in the nucleus of iron. So the 56 is called the mass number, and it's the P plus N, right? We know that the protons are positively charged, so this nucleus has a positive, well, we'll talk about that in a second, okay? So there are a combination of 56 particles in the nucleus, and they're about equivalent in mass. So the mass number is 56. There's not very much difference between the mass of a proton and a neutron. This number down here is even more important, okay? This number down here is called the atomic number. So that's the atomic number, and that's the mass number. Okay. Well, what's the atomic number? The atomic number is just the protons. So, for whatever reason, instead of giving you the protons in one place and the neutrons in another place, they give you the protons down at the bottom of the symbol, and they give you the mass number up at the top of the symbol, which is the protons plus the neutrons. So how do you figure out how many neutrons you have? You just subtract. So the difference between these two, 56 minus 26 is equal to 30. This particular version of iron is going to have 30 neutrons, okay? And then the last thing is, around the outside of the iron atom, there's going to also be 26 electrons, right? Because electrons are negatively charged. So each atom, an atom like iron here, that has no net charge on it, must have an equal number of electrons as it does protons. So again, when you see something like this, the protons are going to be written equal to the atomic number. If the atom is neutral, like it is in this case, there's no additional charge on it, the electrons are going to be equal to the protons, so P is equal to E. So this guy has P equal to 26, E equal to 26. And the neutrons, the third species, is going to be the difference between these two, and that's going to be 30. Okay, so we're going to do that for all of these examples really quickly here. Okay, all right, so way down here, the simplest element on the whole periodic table, this is a heavier version of hydrogen. Usually you find hydrogen in this state, H11, so that it would have one proton, one electron, right? Because the electrons have to be equal to the protons since there's no charge on it. And 1 minus 1, this particular version of hydrogen has 0 neutrons. It's the only isotope that has 0 neutrons. So that's what those ones mean. This guy over here is a heavier version of hydrogen. It's going to have 1 proton, and 1 minus 1 is 1 neutron, and then also 1 electron. So this version of hydrogen, this isotope of hydrogen, has 1, 1, 1. Okay, here's the next element higher, helium. This version of helium, 3 minus 2, right? 3 minus 2 gives you 1. So this one is helium that has 2 protons, 2 electrons. Remember, the electrons and the protons are going to be equal. And 3 minus 2 would have 1 neutron. So I'll put that over here. 2p, right? Because that's the atomic number. 2e. So you're getting the idea. 2e. And 3 minus 2 will give you the neutrons, 1 neutron. So what's happening here is that the most stable nucleus among these three right here is this guy here. Helium-4 is amazingly stable next to helium-3 and hydrogen. So if you can smash atoms together and get their nuclei to fuse together, you can release energy because this guy is much more stable than this guy. So let's see what happens if we add these two things together in a nuclear reaction. I'll get a little piece of paper for that. Let's see if we can make helium-4 out of hydrogen 2, and maybe it releases something. So let's try to fuse together hydrogen 1, 2 plus, what happens if it gets together with a, oh, let's get it together first with another hydrogen 1, 2. So this would be 2 hydrogens if you could do that. Okay. So this is a particle that has 1 proton, 1 neutron, 1 electron. This is a particle of 1 proton, 1 neutron, and electron. If I could smash them together and fuse them together, then this plus this adds up to 2, and this plus this adds up to 4. Right? So the mass number would be 4, and the element that has a atomic number of 2, the atomic number defines which element it is. Anything that has 2 protons is helium. So what I've done is I've fused together a hydrogen, a deuterium, a sort of heavier version of a hydrogen with another one of those. It makes helium, and it gives off a ton of energy. This would be an exothermic process. This is what's happening on the sun all the time, is you're fusing these smaller elements like this guy or this guy, and you're releasing energy because the binding energy, when the atoms are tightly held together and the nuclear bonds are very strong, the excess energy gets released into this. So you can have this reaction going on and extract the heat and use it to make electricity in the traditional sense of boiling water. Okay, so this would be a fusion reaction. Okay, we haven't been able to harness that efficiently on Earth yet, but it's definitely happening on the sun, and it's huge. Look how much different it is from here to here. The one that we've been able to harness is the other way. Take large unstable nuclei, like this one over here for uranium-238, and decompose it into smaller things like iron, and that also releases energy. Okay, it releases energy because these bonds are stronger than those bonds. So where does the excess energy go when you get the tighter formation? The excess energy can be used to make electricity, right? Again, you boil water, make steam, steam turns the turbine. So anything in this direction makes energy, anything in this direction makes energy. Okay, fusing small atoms together to deliver energy is called fusion. Right? So fusion, again, happens on the sun, okay? Happens in the stars. We can do it on Earth in terms of people have been able to develop nuclear bombs that work on fusion, but we've never been able to harness it to generate electricity because it's very hard to control, right? You have to put a huge amount of energy in to get this huge amount of energy out, but we haven't been able to keep it hot enough and develop a reactor system to have a continuous process of fusion, right? We can get it to occur in a bomb for a hundredth of a millionth of a second and release all that energy, but we haven't been able to figure out how to control it, right? Because what vessel do you put it in? It would melt the walls of any vessel. So we'll talk about that a little later on. So this is the holy grail of energy. If we could figure out how to harness nuclear fusion, because the other thing is you don't get any nuclear waste, right? This is not bad stuff, helium. Okay, So let's talk about the practical one, or the one that's been going on for the last 80 years, right? Since 1940. And that is the idea of man harnessing nuclear fission. And we'll talk about that in a second. So fission is the breaking up of larger things like uranium is a classic, right? 298, excuse me, 238. Okay. And that uranium-238 decomposing, and I'll tell you what its fusion fragments are in a second. I'll look those up real quick. It doesn't matter so much. They don't really go on and do anything else. But since we have it, I might as well show you. All right, well, I guess we could actually backtrack it. If we are going to make, if one of them, we can figure out what the other one is. Okay, so let's do this. If we know that we're going to make iron 56, okay, and I'll just plus whatever the other guy has to be, so I know I'm going to make iron 56. So if I take 92 and take away 26, I have to get the atomic number of the other part. So 92 minus 26 gives me 66. So if I was able to do this, okay, I can look what that element up is in a second. And if this is 56, I can subtract this guy from this guy, and that has to be the total mass of the other element, because you always have conservation of mass. These atomic numbers add up, and these mass numbers add up. So if this one is 56, 238 minus 56 will give me the mass of the other guy. So 238 minus 56 gives me 182. Well, actually, I got a feeling this would be an unstable thing with 182 on there, probably. But if I could do this, this one would also give me energy, because these two things are more stable than the original thing. So breaking up large atoms. Okay, so I'm going to look that guy up for you. Who's number 66? '66 is DY, which is named after Freeman Dyson, Dysonium. Okay, so you'd make those two things. Okay, so this guy, if you could do this, okay, this is probably not the fragments that it makes, but this guy would also release energy, okay, because I'm making more stable substances. This guy probably decomposes into two other particles. Those are called daughters. Okay, so what is this? Take-home lesson: fission, putting things together. Fusion, putting things together, and then nuclear fission, breaking them apart. Okay, here's a breaking apart reaction. Both of them are exothermic. They could be harnessed for energy. Right now, in the world, we're only using this one to make commercial nuclear power. Okay, we haven't been able to. This is just in the research phases, and we'll talk about that a little bit later on. Okay, so that's really important, this idea. Study this chart. You should probably take a picture of it, right? Anytime you move towards this middle group, you release energy. These guys are the lowest in energy. I know it's opposite. We usually do it downhill, okay? But these guys are going to be the most stable, these guys in the middle here, okay? And then the other thing we just learned is this atomic number tells you what element you have. Uranium is the only element with 92 protons. And the number up here is the protons plus the neutrons in the nucleus. And the electrons, which are on the outside, which really don't have anything to do with the nuclear reaction, in this case, would be equal to the number of protons. So this guy has 92 protons, 92 electrons. This guy has 26 protons, 26 electrons, 2 protons, 2 electrons, 2 protons, 2 electrons, 1 proton, 1 electron. And how do you get the neutrons? You just subtract these two. The difference between these two is the neutrons. Good? Okay. Very important, this chart here. It's called a curve of binding energy, a plot of binding energy per nucleus versus the mass number. Individual isotopes may lie slightly off the general curve, as helium-24 does. Arrows indicate the energy release path for nuclear fusion and fission. Okay. Okay, so that being said, let's talk a teeny bit about the history. So before I go into what's in the notes, I just want to refer you to the first time, okay, the first time that a fission reaction was conducted in which a chain reaction was sustained for any period of time was done in 1941, in December of 1941, by a group of scientists at the University of Chicago, led by Italian scientist Enrico Fermi. So it was called Chicago Pile 1. It was in the basement, I think, of the gym at the University of Chicago, which, you know, doesn't get the same name recognition as Harvard or Yale, but is one of the great universities in the United States. So Enrico Fermi, who was born in Italy in 1901, won the Nobel Prize for Physics, specifically talking about nuclear physics, in 1938. And he, right after he won the Nobel Prize, he quickly left fascist Italy to come to the United States because he wasn't a fascist, okay, and he wanted to be on the Allies' side. So he got a job as a professor at the University of Chicago. The United States was thrilled to have him. Many of the other famous scientists from Europe, like Einstein, also came to the United States or to Canada to escape either Germany or Italy at that time. So just a few years later, in the basement, he was able to build an atomic pile, and it literally was a pile of lead moderator material with holes in it that the nuclear uranium was placed inside of it, and there were also control rods placed inside of this pile. So they basically piled up stacks of lead with cores of uranium inside of them, and they played around with the arrangement to figure out what pile they could put together to give them a continuous nuclear reaction that where a chain reaction occurred. Okay, so which type of nuclear energy is this? This is going to be the fission type, right? So he's responsible for putting together the first chain reaction or fission reaction based on the decay of uranium. Okay, so what am I going to show you then? So after that started, what I'll do is I will go through some of the figures in a second, but the first application, the bad thing, right? But the first application of a sustained chain reaction was within a few years of that. By 1945, the United States and its allies were able to build the first atomic bombs based on this research. And those atomic bombs were used twice in Japan to end World War II. But after that, people realized, you know what, there is a positive practical application of nuclear reactions where we can generate electricity from the heat energy that's lost from these exothermic reactions. So a group called Atoms for Peace program was started under the Eisenhower administration in 1957. And from that point on, the United States started to put serious energy and time into figuring out how to make electricity out of from nuclear processes, specifically from the fission process. Okay, so it's all based, same thing with the nuclear pile, it's all based on this idea of a chain reaction. So a neutron that's escaping another uranium-238 someplace, and now this neutron is going to escape naturally, okay, smashes into a U-235, uranium with 235 nuclei in it, So I'll just give you that breakdown of that guy. It's a slightly different isotope than I talked about before. I was talking about U-238. Well, U-235 is important because it's actually the fissionable material. It's the one that you can get to go through this chain reaction. Okay, although U-238 is unstable, you're not able to set up a chain reaction as you are with U-235. So that's why U-235 is going to be so important. That's why we're going to have to enrich our naturally occurring uranium to get the percentages of U-235 higher than they naturally would be. At their natural concentrations, they're not high enough to sustain this nuclear reaction. Okay, so if you get it up to about 4 or 5%, then this reaction will take off. So let me describe what this nucleus is first. All uranium has 92 protons. That's the atomic number for uranium. So there's 92 protons. There's also 92 electrons. We don't care about the electrons. They're zipping around the outside here. They're not going to participate. These are nuclear reactions that we're talking about. Okay, so how many neutrons does this thing have? Well, the way you calculate the neutrons is you take the 235 minus the atomic number 92. Remember, uranium's always 92. So 235 minus 92 gives you 143 neutrons. So this is the fissionable particle. Here comes another neutron from the outside with kinetic energy, smashes into it, breaks it apart to form, these are called fission fragments. Those are what we saw in the last example, right, where we specifically broke up our uranium-238 into iron and this other particle, plus the energy. And where's the energy? It's in the kinetic energy of these things smashing and breaking apart, okay? But the more important thing is, in this particular version, uranium-235 also gives you 2 other neutrons, which can go on to hit another uranium, and the process can repeat. So what's happening is here, I blow apart one U-235. In the next step, I blow apart 2, giving me that much more heat. And not only that, more importantly, 1 neutron gives me 2 neutrons, gives me 4 neutrons, gives me 8 neutrons, gives me 16 neutrons, and it just keeps on doubling. Everything keeps on doubling, then to 32, then to 64, then to 128. It just keeps on doubling, right? Let me just make sure I got that right. 64 times 2. Yeah, 128 would be the next one, right? So it just keep until it just all of that heat comes out. So what we're going to try to do is we're going to try to harness this so that it doesn't go crazy and go exponential, but that we can keep the amount of neutrons constant so that they don't decay and go down to 0 and the reaction stops, but they also don't go crazy and exponentially go off so that I get a meltdown or something terrible or a bomb. So I want to moderate the reaction, control the reaction to just have the number of neutrons that are going in equal to the number that are coming out and just stay at a sustained rate of reaction. And then at that sustained rate of reaction, I can capture the excess heat, use it to boil water, and make electricity. So this is going to be the most important reaction that we're going to talk about. I'm not specifically, I don't care what these fusion fragments are, right? It's the energy that I'm interested in and the excess neutrons. Again, we want to do something like that. We want to figure out a way to not have it go crazy, to be an uncontrolled chain reaction, but to get a controlled chain reaction where I keep the amount of neutrons equal and I keep on getting the heat out. Okay, so we'll talk about the way you set up the reaction to do that. Okay, here's 2 different reactors that I'll show you from this same old textbook, which is 14.2 and 14.3. Just have to go back a little bit. which ones are 14.2 and 14.3. This is 14.5. This is kind of cool. So in the United States, here's where the operable nuclear power plants are located. So you see 1 in Washington, 4 in California, a lot in Florida, Texas. Look at South Carolina, my goodness. North Carolina, Pennsylvania. Okay, New Jersey's got, this diagram shows shows 2, but we really have a little bit more than that. I believe we have 4 on it. And in New York, in upstate New York, okay, 1 in New Hampshire, 1 in Vermont. Look at Illinois. So some states have gone heavily into nuclear. It looks like Illinois, right, where they probably generate most of their electricity from a nuclear power plant. Some not at all. Look at West Virginia, which is a coal state. And out in the far west, no nuclear reactors in the Rocky Mountains whatsoever. So that's kind of neat. So it's kind of states' decisions, right? They have to get a license from the United States, but if they're going to invest, the money has to come initially from those utilities, right? So some states have gone more heavily into nuclear than others. How about the world scene? Now again, what kind of nuclear reactors are these? They are 100% all fission reactors. We've not been able to take advantage of fusion yet. Nowhere in the world has anybody made a sustained fusion reaction. Okay, so let me just make this a teeny bit smaller. This is kind of cool. This is the nuclear share of the national electricity. Okay, so Lithuania, okay, makes 76%. Right? 76% of its electricity in Lithuania is made by nuclear power. France, second place with 75%. You work your way down. You see a lot of these are former Soviet republics. Ukraine, 49%. Armenia, 45%. It's very interesting that Russia is only 18%. So they went heavily nuclear in the other satellite states when they were the USSR, not so much in their own country, which is really kind of interesting, right? Because they didn't want to put it near Moscow or something like that, but they were willing to put it near Kiev, which is kind of terrible, okay? Sweden, 37%. Again, some countries have done it very responsibly, some countries not so much. Here's the United States at 20% of our total energy is generated from nuclear power. United Kingdom, England, 18%, all the way down to India, Pakistan, Brazil, among the smallest. Very interesting how one European country did not get into this whatsoever, and that was Holland, which is the Netherlands. I also don't see Italy on here, and I don't see Spain on here, which is interesting. So they might have even be below here. Canada, 15%. Oh, here's Spain. Spain, 17%. Anybody see Italy? No Italy. Okay. Okay, but most of the European countries then have some nuclear footprint. Good. How about Japan? We see Japan on here? 29%, so higher than the United States. Okay, Japan and Germany, both 29%. So percentage of energy generated by nuclear reactions. So we reviewed the nuclear power plants in the U.S. We reviewed the percentage of electricity generated from nuclear power in the world. And here's our these are going to be our 2 chain reactions that are going to be critical. Now, we don't get to control which ones happen. If you set up a nuclear reactor and you take the uranium 238 that is naturally occurring as only about 0.7% uranium 235 mixed in with the uranium 238, which is naturally occurring. So that means it's going to be 99.3% the guy that doesn't undergo this reaction, right? These 2 reactions will occur. One reaction that can occur, okay, and you can figure out what the probability of this one happening versus this one, but you can never tell on a particular atom which way it's going to go. But overall, you can say, okay, most of them go this way, maybe 70% go this way, and 30% go this way. Okay, but if a neutron strikes uranium-235, it can break up into barium-143, krypton-91, plus two neutrons, right, which are important to keep the reaction going. You need at least one to set up a chain reaction so that this neutron can swing back around and hit another U-235, and we're going to see that in lab. Plus the heat, right? The heat that comes out in the form of kinetic energy of the molecules is critical because that's what we're going to use to boil the water to make electricity, right? There's no way to take this and make electricity directly. I don't see any electrons coming out. It's not an electrochemical process. It's just old-fashioned heat. All right, second reaction that happens is maybe the neutron hits a U-235, and instead of it breaking up into these two fragments and two neutrons, it breaks up into these two fragments. Look, slightly different mass here, okay? This guy's exactly the same, so the one extra neutron, this guy gave off 3 neutrons, this guy gave off 2. Now, notice, neutrons, guys, add up on the top. So 142 plus 91 plus 3 should give you 235, okay? These neutrons have no protons, right? So this is the number of protons. 56 plus 36 will give you 92, okay? So that has to be the case here. I didn't write it, but remember, uranium is always 92. That's its atomic number. Good? All right, here's the problem. The uranium-235 that we find in the world makes up only about 0.7% of the uranium in the Earth. So we have to enrich it. You need to enrich it to 2 to 4% in order for the chain reactions to be self-sustaining, right? Go back to that critical picture just to keep that reaction going, right? Keep that reaction going and keep at least one neutron per cycle alive to go and hit another uranium-235. The reactor can't explode like an atom bomb because it does not contain a critical mass of uranium-235. So a misconception that people have is that at the nuclear power plant, if it goes out of control, there could be a nuclear explosion. That's impossible. There's not enough fissionable enough material on site for that to happen, right? It's not physically located close enough for the chain reaction to continue to the point where an explosion could occur. A lot of other bad things can happen, right? Like there could be a pump failure, and then a loss of the nuclear material can go out to the outside, but you're not going to have a nuclear explosion like you would have in a bomb. Okay? The critical mass of uranium that needs to be assembled into a sphere. Now this has to be the fissionable uranium, the U-235, right? So this shouldn't just say uranium. This should say uranium-235. Has to be 10 kilograms, okay? So we never have 10 kilograms all close together, tight in a sphere, right? Like that would look like a softball of fissionable material, because that could go critical, and an uncontrolled chain reaction could occur to the point where a nuclear explosion could occur. So the geometry, this sphere is the geometry that allows the fewest neutrons to escape, is that in a sphere. We're not going to build our nuclear power plants. If you see the way Enrique Fermi first built the one in Chicago, even up to this day, we don't tend to build them in a spherical form. We tend to build them in rods of nuclear material, so that they're much more easily controllable. And I'll show you that geometry in a second. Okay, so nuclear weapons, though, are built into 2 half spheres, hemispheres, right? And then the 2 half spheres are smashed together either with a chemical bomb on the outside to push these 2 things together, and that's how I get the fissionable material all in one place. But again, in order to do that, right, in order to make a nuclear weapons, you have to enrich the uranium all the way up to 90%. way different than the 3% that you need in a nuclear reactor. So that's a good thing, right? That these two numbers are so far apart, right? 90% to make a bomb, just 3 to 4% enrichment in order to make a nuclear power plant. Okay, so there's going to be two types of reactors that you're responsible for, a BWR and a PWR. The BWR is the simpler type. It's probably the more prevalent type in the world. It's called a boiling water reactor. The PWR is a pressurized water reactor. Instead of the boiling water that flows right through the atomic pile being used to generate electricity, high pressure water is heated, and that water then goes through a heat exchanger and boils secondary water, and that water generates the electricity. So you're just one stage further away from the nuclear reactor. In this one, you're actually going to boil the water, make the steam right in the atomic pile. In this one, you're going to make heat. You're going to remove that heat with a heat exchanger, pump that pressurized hot water around, and that pressurized hot water is going to do what? It is going to boil a secondary water, and you're going to make electricity out of that. Okay, so I'm going to show you those two in a second. Okay, here's some pieces. The rest of the page is stuff that you need in order to build a nuclear reactor. So you need fuel rods that contain the 3% uranium-235 in them, that they've been enriched with 3% U-235. So it's 97% U-238 in the fuel rod, okay, and 3% uranium 235, the fissionable kind. Then you also, if the fuel rods are going this way, in between the fuel rods, you need to put control rods that can be slipped in and out to capture the extra neutrons. And those tend to be made out of cadmium or boron. So the fuel rods are made out of uranium that's been enriched up to 3%. So the other 97% is uranium-238. Okay? And then the control rods are cadmium or metal or boron. Okay? So those are solid pipes, they look like, only solid rods that you move in and out of the nuclear material to capture extra neutrons so that it can't go to an uncontrolled nuclear chain reaction. You want to have a controlled chain reaction. So we now have computers that move the rods in and out based on how many neutrons the detectors see in the nuclear pile. Okay, so these are materials, the control rods are materials with a very high cross-section, which is just a term which means the high ability to capture or absorb neutrons. So if a neutron goes through the control rod, it's 99% going to get captured by the control rod and then render it harmless. So you can shut the reactor off completely by pushing the control rods all the way in. Okay, last thing you need, so you got fuel rods, you got control rods, you need a moderator. And the moderator is usually just simple, they call it light water, which is just regular water, H2O. Heavy water would be water with a heavier isotope of hydrogen on it, D2O, but we don't need heavy water. Ours are going to be light water reactors. Okay, so what does water do? Two critical functions that you're responsible for. Okay, it slows down the neutrons. Okay, and the reason is if the neutrons, when they originally come out of the fission process, they're moving too fast, and those fast moving neutrons are less likely to be captured by another uranium-235. Okay, the efficiency for fission is much better when the neutrons are going slow. So if we slow them down by making them travel through water, then they're more likely to be captured. Otherwise, if they're going too fast, they'll just hit the uranium-235 and they won't be captured. They have almost too much energy. The second thing that they do, and the reason why we want them to be a fluid, which water is, that we can pump around in a circle, is they capture the excess heat and transfer it out of the core. Okay, so all those neutrons smashing into the water molecules, doesn't cause a nuclear reaction with the water molecules, but causes the water molecules to heat up. And that heat then, that hot water can be pumped around in a circle, and you can pull the heat out of the reactor, right? Because we don't want it to literally melt down because too much heat builds up. So you have several pumps and different mechanisms that circulate the water. So the water is the moderator, and we circulate it around the nuclear reactor. Okay, so I'm going to show you the setup for a BWR and a PWR, and then I'll also probably upload a couple of videos related to it. Okay, then the next section we'll do after that is what are two different mechanisms to enrich the fuel, but we'll do that in a second. Okay? So here's